Today, we're diving into the world of production and inventory management. This presentation is all about mastering key concepts like production planning, scheduling, and inventory control, which are essential for achieving operational efficiency. This program has been developed by Dr. Jawad Sebaali. By the end of this training, you'll be able to apply the core principles of production planning, scheduling, and inventory control to everyday manufacturing and supply chain operations. We'll cover how demand forecasting, master production scheduling, material requirements planning, and inventory management all work together to reduce waste and prevent shortages. You'll also learn to spot inefficiencies in your current processes and choose the right planning tools for your specific situation, enabling you to make confident decisions that lead to real improvements in efficiency, cost control, and service reliability. Chapter 1 introduces us to the foundations of production management, which is all about planning, organizing, and controlling the activities that turn raw materials into finished products. This discipline is central to manufacturing operations because it directly impacts cost, quality, delivery times, and ultimately customer satisfaction. Whether you're overseeing a single production line or a whole plant, the decisions you make on capacity, sequencing, and resource allocation are crucial. Production management equips you with the tools to make these decisions confidently, replacing guesswork with informed strategy. The production management cycle consists of 4 key stages: plan, schedule, execute, and control. Planning sets a direction for the entire process, outlining what needs to be done. Scheduling then assigns the necessary resources and time to make that plan achievable. Once scheduled, execution puts the plan into motion, turning ideas into action. Finally, control monitors the results, measuring performance, and feeding any corrections back into the next planning phase. This cycle is continuous, and knowing exactly where you're within at any given moment helps you focus on the right issues at the right time. Here we're looking at 3 common types of production systems. First, make-to-stock, or MTS. In this system, products are made in advance based on forecasted demand and kept in inventory. This approach works well for high-volume, standardized goods where fast delivery is essential. Next is make-to-order, or MTO. Here, production only starts after confirmed customer order, which helps cut down on inventory costs but demands flexible scheduling and accurate lead time management. Finally, assemble-to-order, or ATO, combines elements of both. Standard components are produced and stocked ahead of time, then assembled into the final product once the customer's specific configuration is known. This allows for customization without long wait times. When we talk about production planning, everything begins with understanding demand. Before scheduling any job or order materials, you need a clear and reliable picture of what customers want and when they want it. Demand can come from various sources, like confirmed orders, historical sales patterns, or projections from the sales team, and often a combination of these gives the best insight. It's also crucial to distinguish between independent demand, which is a demand for finished products directly ordered by customers, and dependent demand, the need for the parts and sub-assemblies that go into those finished goods. Mixing these up can cause serious issues, either making too many parts too early or facing shortages that disrupt production at exactly the wrong time. Getting this balance right is key to efficient and responsive production planning. In this chapter, we focus on demand forecasting, which is all about estimating future demand to help plan production, procurement, and staffing ahead of time. While no forecast is perfectly accurate, having a well-structured approach is definitely more reliable than just relying on intuition. There are 2 main types of forecasting methods. First, qualitative methods, which come into play when historical data is limited or unreliable. These include techniques like Salesforce Composite, expert panels, and the Delphi method, where specialists provide input over several rounds to reach consensus estimate. Then, there are quantitative methods, which rely on historical sales data. Techniques such as moving averages help smooth out short-term fluctuations, and exponential smoothing gives more weight to recent data to reflect current trends. Regression analysis goes a step further by identifying connections between demand and external factors like seasonality or economic indicators. Finally, managing forecast error is crucial. Metrics like mean absolute deviation or MAD and mean absolute percentage error, MAPE, help measure how far off your forecast has been. By tracking these metrics over time, you can see if your forecasting approach is improving or starting to drift off course. When it comes to practical forecasting principles, the first thing to keep in mind is to use the right time horizon. Short-term forecasts, which cover days to weeks, are essential for scheduling. Medium-term forecasts spanning months help with capacity and procurement planning, while long-term forecasts, covering quarters to years, guide strategic decisions like capital investment. It's important to match your forecasting method to the horizon you're working with. Next, segment your products. High volume. Stable products can often be forecasted statistically, but low volume or highly variable items usually need judgment-based input from sales or customers. Relying on one forecasting method for every SKU can lead to systematic errors. Finally, integrate demand signals from multiple sources. Customer orders, promotional calendars, and market intelligence all provide valuable information. A forecast created in isolation from the sales team is almost always less accurate than one developed collaboratively. This integration is key to improving forecast reliability. Chapter 3 focuses on aggregate production planning, which is all about translating the demand forecast into a practical medium-term plan. This plan covers key elements like production output, workforce levels, and inventory targets. Unlike detailed planning at the individual SKU level, aggregate production planning works at the product family level, making it manageable for decisions over a period of 2 to 12 months. Essentially, it answers 3 crucial questions: how much to produce each period, how many people are needed, and how much inventory to hold as a buffer. Getting this balance right is vital to avoid both idle capacity and missed orders, which can be very costly. The goal is to optimize resources and meet demand efficiently over the planning horizon. When it comes to aggregate planning strategies, the key is to choose the one that aligns best with your cost structure. The chase strategy is particularly effective when overtime and hiring costs are low compared to the costs of holding inventory. On the other hand, the level strategy works best in situations where skilled labor is hard to find and expensive to replace. In reality, most operations don't rely solely on one approach. Instead, they use a mixed strategy that balances the strengths of both to optimize efficiency and costs. The Master Production Schedule, or MPS, serves as a crucial bridge between aggregate planning and the detailed schedules that guide the shop floor. It clearly defines which finished products will be produced, in what quantities, and during which time periods, typically over a rolling horizon of weeks or months. First, it's essential to define the planning horizon. This period should be long enough to cover procurement lead times and enable meaningful capacity decisions, but also short enough to stay actionable and responsive to changes. Next, input the demand data by incorporating confirmed orders, forecasts, and safety stock targets. The MPS must be based on actual demand signals, not just theoretical targets detached from the market. Finally, check capacity feasibility. An MPS that exceeds available capacity isn't a real plan. It's wishful thinking. Using rough-cut capacity planning helps ensure your schedule can realistically be executed. Rough-cut capacity planning, or RCCP, is a tool that helps us check if our critical work centers have enough capacity to meet the master production schedule. It does this by using a simplified model called a bill of resources, which lets us spot potential bottlenecks early on. before they disrupt operations. Unlike detailed capacity planning, our CCP works at a higher level and is much faster to run and easier to understand, which is exactly what we need during the planning stage when decisions can still be changed. When our CCP shows a capacity gap, we typically have three options: shift some production to other periods, authorize overtime at a constrained work center, or outsource part of the workload. It's important to document the choice and the reasoning behind it, as this information helps improve the next planning cycle. Material Requirements Planning, or MRP, is a calculation-driven system that helps manufacturers determine the exact materials and components needed, the quantities required, and precise dates to meet production schedules. It works by breaking down the bill of materials for each finished product and adjusting requirements based on lead times. For example, if a subassembly takes 3 weeks to procure and the final product is needed in week 8, the order for that subassembly must be placed by week 5. This automation allows MRP to handle complex scheduling across hundreds or thousands of parts efficiently. The first essential input for MRP is the Master Production Schedule, or MPS. The MPS tells MRP how many finished units are required in each time period. Without an accurate and stable MPS, every downstream calculation MRP makes will be unreliable. Next, we have the Bill of Materials, or BOM. The BOM defines every component and subassembly needed to build one unit of the finished product, including the quantity of each. Accuracy here is crucial because any errors at the part number level will lead MRP to generate incorrect material requirements. Finally, MRP relies on inventory records. It subtracts on-hand stock and scheduled receipts from the gross requirements to calculate net requirements. Inaccurate inventory records are actually one of the most common reasons MRP systems fail in practice. So, these three inputs, MPS, BLM, and inventory records, must all be precise for MRP to function correctly. Let's look at the key outputs of MRP and what actions we should take with them. First, we have planned order releases. These are the recommended purchase or production orders that MRP calculates to meet net requirements. It's important to review these planned orders carefully before releasing them because demand can change, and once you release them, they become firm orders. Next are reschedule notices. MRP spots orders that are scheduled at the wrong time compared to current needs. If an order is too early, it ties up cash and storage space. If it's too late, you risk shortages. Both situations require immediate attention to keep operations smooth. Finally, there are exception messages. These are alerts generated by modern MRP systems to highlight issues needing human judgment, such as unmet lead times or order quantities below minimum size. Checking these messages daily during your planning review is critical for effective supply chain management. MRP2, or Manufacturing Resource Planning, takes the idea of traditional MRP and expands it significantly. Instead of focusing only on materials, it incorporates all manufacturing resources like labor, machine capacity, tooling, and cash. This integration allows financial planning to work hand in hand with production planning, making the cost implications of every decision visible instantly. One key advancement in MRP2 is the concept of closed-loop MRP. This means the system doesn't just send out plans and forget about them. Instead, it receives real-time feedback from the shop floor. When actual performance doesn't match the plan, the system highlights these discrepancies, enabling planners to make timely adjustments. This continuous feedback loop is crucial because it keeps the planning system accurate, relevant, and responsive to real-world conditions. Chapter 5 focuses on production scheduling. Scheduling is essentially the process of assigning specific jobs to specific work centers at specific times. It takes the quantities and due dates from a master production schedule and translates them into a time sequence list of work orders that operators can actually execute. The goal of good scheduling is to minimize setup times balance workloads across work centers, prevent idle time, and ensure that jobs meet their due dates. On the other hand, poor scheduling leads to queues at bottleneck machines, excessive work-in-process inventory, and a constant cycle of expediting that consumes supervisory time without solving the underlying problem. Forward scheduling starts at the current time and moves forward to determine the earliest possible completion date, which is great when you want to finish quickly and confirm delivery dates early. Backward scheduling, on the other hand, works by starting from the due date and planning backward, which helps minimize inventory by ensuring tasks start just in time. Most plants actually use a combination of both approaches, depending on the specific job and customer needs. This balance helps optimize efficiency while meeting deadlines effectively. Let's talk about some common job sequencing rules that help manage workflows efficiently. First, we have first come, first served, or FCFS. This one processes jobs in the order they arrive, which is simple and seen as fair, but it doesn't consider urgency or how long each job takes, so short jobs might wait longer than necessary. Next up is shortest processing time, or SPT. Here, the job with the shortest processing time goes first, which helps minimize average flow time and reduces the queue, making it great when throughput is a priority. Then there's earliest due date, or EDD, which sequences jobs based on their due dates, prioritizing the most urgent ones to minimize maximum lateness. Perfect when on-time delivery is crucial. Finally, the critical ratio rule divides the time remaining until a job's due date by the work left to do. A ratio below 1 means the job is behind schedule. This dynamic approach adjusts as conditions change, making it one of the most practical choices in real-world settings. The theory of constraints, developed by Eliyahu Goldratt, teaches us that every production system has at least one bottleneck, which is the resource limiting the output of the whole system. Improving other parts that aren't bottlenecks won't increase overall throughput. It just creates longer queues in front of the bottleneck. To manage this, we follow 5 key steps. First, identify the system's limiting resource. Then exploit the bottleneck by maximizing its output without heavy investment. Next, subordinate all other processes to support the constraint, ensuring the entire system works harmoniously around it. Finally, elevate the constraint by increasing its capacity. By applying these steps in sequence, we focus our improvement efforts where they truly make a difference. On this slide, we're looking at 2 key scheduling tools and techniques that help manage production efficiently. First, we have Gantt charts, which display jobs as horizontal bars along a time axis, with each row representing a specific machine or work center. This gives supervisors an immediate visual picture of what is scheduled, what's currently running, and where any gaps exist. For decades, manual Gantt boards were a staple in planning rooms, and today, digital versions are integrated into most ERP and APS systems. Then we have advanced planning and scheduling, or APS systems. These software tools use optimization algorithms to simultaneously consider machine capacity, operator availability, material constraints, and customer priorities. Unlike traditional MRP, which schedules resources independently, APS generates a globally feasible schedule that works best in complex environments with many products, multiple work centers, and tight delivery windows, making it an essential tool for modern manufacturing operations. In Chapter 6, we dive into the fundamentals of inventory management. Inventory is essentially the physical outcome of decisions made earlier in the supply chain. Every single item on a shelf reflects a forecast, a purchase order, a production run, or a policy choice. Inventory management is all about making sure these decisions lead to the right quantities in the right places at just the right time. There are 4 key types of inventory to keep track of: raw materials, work in process or WIP, finished goods, and MRO supplies, which are maintenance, repair, and operations items. Each of these categories has its own unique drivers, cost structures, and priorities when it comes to management. On this slide, we're looking at the three main types of costs involved in carrying inventory. First, there are holding costs. These include everything from the capital tied up in stock to warehouse space, handling labor, insurance, and the risk of spoilage or obsolescence. Holding costs typically range between 20 and 40% of the unit value annually, which makes them a significant expense. Next are ordering costs. Every time you place an order or set up production, there are costs involved, like administrative work, receiving and inspecting materials, and the time needed to switch machines to a different product. While placing larger, less frequent orders can reduce these costs per unit, they also increase holding costs, so it's a balancing act. Finally, we have shortage costs. These happen when inventory runs out, leading to lost sales, emergency purchase premiums, expediting costs, and even damage to customer relationships. Although shortage costs can be hard to put a number on, they often turn out to be the most significant and damaging of all three cost categories. The economic order quantity, or EOQ, is a model used to determine the order quantity that minimizes the total cost of holding inventory and placing orders. This model has been a cornerstone in operations management for over a century because it provides a straightforward yet powerful approach to inventory decisions. The EOQ formula involves three key elements: D, which represents the annual demand, S, the cost to place a single order, and H, the annual holding cost per unit. By calculating EOQ, you find the optimal order size that balances these costs to achieve the lowest overall expense. However, it's important to remember that EOQ works best under certain assumptions like stable demand and fixed costs. In real life, factors like volume discounts, supplier minimums, and storage constraints will require you to adjust the EOQ figure. Still, even a rough EOQ calculation is far more effective than ordering based on habit or guesswork. Let's talk about how to determine the reorder point and safety stock. First, you calculate the average demand during lead time by multiplying your average daily demand by the supplier's lead time in days. This shows you the expected consumption while your replenishment order is on its way. Next, you need to determine safety stock, which is crucial because it covers the variability in both demand and lead time. A common method is to multiply a service level factor, taken from a standard normal distribution table, by the standard deviation of demand during lead time. Finally, you set the reorder point by adding the average demand during lead time to your safety stock. When your on-hand inventory falls to this level, a new order should be placed immediately to prevent any stockouts before the next shipment arrives. Not all inventory items require the same level of management attention. The ABC inventory classification method helps us prioritize by grouping items based on their relative importance, usually measured by annual consumption value. This way, we can focus our control efforts where they matter most. Category A items are small number products but represent a large share of total value. These need tight management, including frequent reviews, accurate forecasting, and strong supplier relationships. The items are more moderate in both number and value, so standard control procedures with periodic reviews work well. Finally, C items make up a large portion of the inventory but only a small value share, so they are managed with simple replenishment rules, larger safety stocks, and less frequent reviews. This classification ensures efficient use of resources and better inventory control. An annual physical inventory count usually causes disruptions and is prone to errors. Cycle counting offers a much more effective approach. Instead of counting everything at once, a small number of items are counted daily on a rotating schedule. This way, every item in the warehouse gets counted multiple times a year, with the most important items counted most frequently. Maintaining a high level of inventory record accuracy is crucial for material requirements planning, or MRP, to generate reliable outputs. When accuracy drops below a certain point, the system starts producing incorrect recommendations, leading planners to override it manually, which defeats the entire purpose. So, consistently building and maintaining accuracy through daily cycle counting is one of the best ways for inventory managers to add value. In this chapter, we explore inventory replenishment systems, focusing on three main types. First, the fixed order quantity system, or Q system, where a predetermined quantity is ordered every time inventory hits the reorder point. This means the order size stays the same, but the timing changes depending on demand. It's ideal for 8 items, where maintaining tight control and consistent orders help manage supplier relationships and cash flow. Next, the fixed order interval system, or P system. Here, orders are placed at regular time intervals, but the order size varies to reach a target inventory level. This approach simplifies coordination with suppliers and can cut freight costs by combining multiple items into one shipment. Lastly, the min-max system blends the two. When inventory falls to a minimum level, an order raises stock back to the maximum level. This is a straightforward method often used for C items and MRO supplies, where ease of management takes priority over precise inventory optimization. In this chapter, we focus on lean manufacturing and production efficiency. Lean manufacturing, which originated from the Toyota production system, is fundamentally about identifying and eliminating any activity that uses resources but doesn't add value for the customer. It's important to understand that lean is not just a cost-cutting program. Rather, it's a mindset that rethinks how work flows through your production system. By applying lean principles consistently, companies achieve faster throughput, lower inventory levels, improved quality, and a more engaged workforce because problems are brought to light and addressed directly, not ignored or worked around. This approach ultimately drives a much more efficient and responsive production process. On this slide, we focus on 3 key types of waste from the 7 wastes, or muda, in lean manufacturing. First, transportation and motion. Moving materials or people more than necessary adds both time and cost without creating any value. It's important to regularly review your plant layout to minimize travel distances for materials and operators. Next is inventory and overproduction. Producing more than needed or holding excess stock ties up cash and can disguise quality issues. The best approach here is to reduce batch sizes and synchronize production with actual demand. Lastly, waiting and defects represent significant wastes. Idle time between process steps and rework due to quality failures both indicate processes that lack control. These issues highlight the need for better standardization or error-proofing to keep the process running smoothly. Just-in-time production focuses on making and delivering the right product in the right amount exactly when it's needed and not before. This approach minimizes inventory to the bare essentials, which means every step in the supply chain must be dependable and predictable. Now, a key tool in this system is the Kanban. It acts as a pull signal, usually a card or bin, that gives a go-ahead to produce or replenish a certain quantity of an item. Without a Kanban signal, nothing is made. This pull system replaces the traditional push method, helping prevent overproduction and making inventory levels clear and visible to everyone on the shop floor. Value stream mapping is a powerful visual tool that helps us track every step in the flow of material and information, all the way from raw material to the customer. What makes it especially useful is that it clearly distinguishes between steps that add value and those that don't, so we can see exactly where time is being spent without benefiting the customer. First, we map the current state by documenting every process step and flow. Then, we identify waste and gaps by highlighting non-value activities and delays. After that, we design a future state that creates an optimized, waste-free flow. The key here is that the current state map shows reality as it really is, while the future state map reveals what the process could look like once waste is removed. The difference between these two maps becomes the foundation for your improvement plan. Also, value stream mapping works best when done by the people involved in the process, not just an external team working from data alone. In this chapter, we're focusing on capacity management. Capacity refers to the maximum rate of output that a work center or facility can achieve under specific operating conditions. Managing capacity effectively means making sure that the available capacity aligns with planned production needs without having too much excess that wastes resources. It's important to remember that capacity is both finite and perishable. For example, an hour of unused machine time today is gone forever. This reality makes accurate capacity planning crucial, because any idle capacity still incurs fixed costs without bringing in revenue, while overloaded capacity leads to bottlenecks, delayed deliveries, and unhappy customers. Balancing these factors is key to ensuring smooth operations and customer satisfaction. Here we see the 3 key levels of capacity planning that help organizations manage their production capabilities effectively. First, resource requirements planning looks at the long-range picture, assessing whether the overall production plan is feasible with the existing and planned facilities. This level helps guide major decisions like capital investments or facility expansions. Next, rough cut capacity planning takes a medium-range perspective by checking critical work centers against the master production schedule. This step is important for spotting capacity mismatches early enough to adjust through options like overtime or subcontracting. Finally, capacity requirements planning, or CRP, dives into the details with work order level calculations for each work center in every period. This detailed analysis ensures the shop floor schedule can actually be executed and helps flag specific overloads so they can be resolved before they become a problem. Overall equipment effectiveness, or OEE, is our key metric for understanding how well a production resource is being utilized compared to its full potential. It combines availability, performance, and quality into a single percentage, giving us a clear picture of where capacity is being lost. Availability at 90% measures the percentage of scheduled time the equipment is actually running, with downtime from breakdowns or changeovers lowering this number. Performance sits at 95%, showing the ratio of actual output to the theoretical maximum, influenced by speed losses and minor stops. Finally, quality is at 99%, representing the proportion of products meeting specs on the first pass, where rework and scrap reduce effective output. Together, these factors help us pinpoint improvement opportunities. Chapter 10 focuses on supply chain integration, which is crucial because production planning never happens in isolation. What goes on in your facility depends heavily on how reliable your suppliers are, and in turn, it influences your customer's experience. Supply chain integration means making sure plans, information, and processes are aligned across the entire network, so a decision made in one place doesn't cause unexpected problems elsewhere. A classic example of what happens without good integration is the bullwhip effect. This is where small changes in customer demand get magnified as they move upstream through distributors, manufacturers, and suppliers, leading to big, costly swings in inventory and production. One of the best ways to reduce this effect is by sharing demand information directly with your suppliers, creating a smoother and more responsive supply chain. Let's talk about supplier relationship and lead time management, starting with reducing supplier lead times. Lead time is basically the time between placing an order and receiving the material. When lead times are shorter, you benefit from smaller safety stocks, quicker responses to demand changes, and less risk from forecast errors. To achieve this, collaborate closely with your suppliers to understand the factors that affect their lead times. You can then work together on specific strategies like blanket orders, consignment stock, or vendor-managed inventory arrangements to shrink those lead times. Now, moving on to supplier performance measurement. It's crucial to track key metrics such as on-time delivery rate, quality acceptance rate, and lead time variability for each critical supplier. By consistently measuring these areas, you create accountability and gather objective data that support supplier development conversations. This data also helps you determine which suppliers are reliable enough for just-in-time replenishment and which ones may require you to keep larger safety stocks as a buffer. Efficient supplier management in these areas can significantly improve your overall supply chain performance. Sales and Operations Planning, or S&OP, is a monthly process that brings together the sales, production, inventory, and financial plans into one unified set of numbers. The goal is to ensure that everyone in the company shares the same understanding of demand and supply, so decisions are made with full awareness of their impact across departments. The process includes several key steps. First, the demand review, where forecasts and customer insights are validated. Then there's a supply review, which looks at capacity, constraints, and plans. Data gathering is critical, collecting sales, inventory, and finance information to support these reviews. Next comes the pre-S&OP meeting, where any gaps are identified and recommendations are developed. Finally, the executive S&OP meeting approves the aligned plan and necessary actions. While S&OP doesn't eliminate conflict between functions, it shifts those conflicts from the production floor to the meeting room, allowing them to be resolved through informed discussion rather than reactive firefighting. In this chapter, we're focusing on ERP systems and their crucial role in production and inventory management. ERP, or Enterprise Resource Planning. Systems bring together all the core business processes of a manufacturing company into one unified software platform. This integration means production planning, inventory management, purchasing, sales order management, and financial accounting all work from the same database. So, when a change happens in one area, it's immediately reflected everywhere else. Some of the most popular ERP platforms used in manufacturing include SAP, Oracle, Microsoft Dynamics, and Infor. However, it's important to remember that the effectiveness of any ERP system hinges on the quality of the data entered. If the inventory records are inaccurate or the bills of materials are outdated, the system will produce plans that are difficult to trust and execute. Accurate data is the foundation for a successful ERP implementation. Let's talk about how to really get value from your ERP system. First, investing in data quality before and after go-live is crucial. Clean and accurate master data, like item records, bills of materials, routings, and inventory balances, is a foundation of great ERP performance. Establishing a strong data governance standard and treating it as an ongoing operational discipline rather than a one-time project is key. Next, focus on training your people not just on the software screens, but on the underlying processes. When users understand the planning logic behind the system, they can better diagnose and fix issues instead of just knowing which buttons to click. Finally, always review system recommendations before acting on them. Early on especially, planners should verify ERP-generated replenishment suggestions because the system's accuracy depends heavily on the correct parameters, which need regular updates as demand and supplier behaviors change. This careful oversight helps keep your ERP working effectively over time. Here we have a real-world case study on Toyota Motor Corporation, focusing on production planning in practice. Toyota, founded in 1937, developed the Toyota Production System, or TPS, which is now considered a global benchmark for manufacturing efficiency. TPS is based on two key principles: Jidoka, which means building quality into process by immediately detecting and stopping defects, and just-in-time production, which means producing only what is needed when it is needed and in the quantities needed. One of the standout features of Toyota's production planning is their use of a pull-based Kanban system. This system controls the flow of materials and inventory by ensuring each production step creates only what the next step requires. This approach prevents overproduction and makes inventory levels transparent for every worker and supervisor on the floor. Toyota's methods have been widely studied and documented since the 1970s, showing their lasting impact on manufacturing worldwide. Keep in mind, this information is based solely on publicly available sources and is shared here for educational purposes. One key lesson from the Toyota case is to standardize before you automate. Toyota made sure to standardize its work processes and quality checks first, because applying technology to an unstandardized process only speeds up the creation of defects. So, it's crucial to write your standard operating procedures before deciding which steps to automate. Another important point is to make problems visible immediately. Toyota uses something called the and cord, which lets any worker stop the production line as soon as they see a defect. This shows how much Toyota values finding problems early, even if it means disrupting the workflow temporarily. Finally, improvement is everyone's job at Toyota. Their Kaizen philosophy means that every person, from the assembly worker to the plant manager, is expected to identify and suggest improvements. This isn't just a program, but a fundamental part of how work is done every day. These lessons together create a culture of continuous collective improvement. In this chapter, we focus on performance measurement in production and inventory management. The key idea here is that you cannot manage what you do not measure. Performance measurement provides crucial feedback, showing if your plans are on track, identifying areas where performance is lagging, and guiding necessary corrective actions. It's important to remember that the goal isn't just to generate reports, but to support informed decisions. This means every metric track must have a clear owner, a specific target, a schedule for regular review, and a documented plan for what to do if performance deviates from acceptable limits. Let's look at some key production and inventory metrics that are essential for effective operations. First, we have OE, or overall equipment effectiveness. This metric combines availability, performance, and quality to give us one clear measure of production efficiency. Next is OTIF, which stands for On Time and Full Delivery. This tells us whether customer orders are delivered both on time and in the correct quantity, making it a direct indicator of service reliability. Then there's IRA, Inventory Record Accuracy, which reflects the percentage of inventory locations where the physical count matches what's in the system. This accuracy is foundational for reliable material requirements planning. Finally, we have DSI, or Days of Supply, also known as inventory turns. This metric shows how many days of demand our current inventory covers, or how often inventory turns over annually, helping us balance service levels with working capital efficiency. Continuous improvement in operations is all about making ongoing, incremental changes that lead to better performance over time. At the heart of this process is the PDCA cycle, which stands for Plan, Do, Check, Act. You start by planning a change based on a diagnosed problem. Then you implement that change on a small scale. Next, you check to see if the change brought the expected results. And finally, you act by either standardizing improvement or adjusting your approach if needed. This cycle, done repeatedly, creates gains that are much more sustainable than occasional big projects. Another key tool is root cause analysis. When a problem arises, the obvious cause you see first is rarely the true underlying issue. The 5 whys technique helps by asking why something happened, then why that cause happened, and so on, digging down through at least 5 layers until you uncover the real root cause. Addressing this root cause is essential because simply fixing the visible symptom often means the problem will come back in a different form. This approach helps us solve problems more effectively and prevent them from recurring. Chapter 13 focuses on digital tools and Industry 4.0 in production management. The manufacturing environment is rapidly evolving as digital technologies open up new possibilities for planning and managing inventory. While these technologies don't replace the fundamental principles we've discussed, they dramatically increase the speed and precision with which we apply them. Key innovations include real-time data collection via connected sensors and IoT devices, predictive analytics that can forecast equipment failures before they happen, and digital twin technology, which lets planners simulate schedule changes virtually before implementing them on the factory floor. These advancements are transforming how production management operates in today's industry. Here we focus on 3 practical digital tools that operations teams can leverage to improve efficiency and accuracy. First, barcode and RFID systems use automated identification to capture inventory movements in real time. This eliminates manual data entry errors and improves inventory accuracy. RFID, in particular, allows tracking without line of sight, making it ideal for fast-paced environments. Next, cloud-based planning platforms provide a unified view of inventory, capacity, and orders across multiple sites. This not only simplifies management, but also lowers IT costs compared to on-premise systems. Plus, it enables smaller operations to access advanced planning tools that were once exclusive to large enterprises. Finally, demand sensing and machine learning bring a new level of precision to forecasting. By analyzing large volumes of data, like point-of-sale information, web traffic, weather, and social media, these algorithms can significantly reduce forecast errors, especially for high-volume consumer products with complex demand patterns. Together, these tools help operations teams work smarter and more responsibly. Let's wrap up with the key learning points from our discussion. First, planning starts with demand. Every production and inventory decision hinges on a clear demand signal. Your forecast and master production schedule really set the stage for everything that follows. Next, MRP acts as the crucial link that connects demand to materials and capacity by translating the master production schedule into specific material needs and purchase orders. But remember, its effectiveness relies on accurate bills of materials, routing data, and inventory records. Then, scheduling plays a vital role in determining what gets done and when. Using sequencing rules and managing bottlenecks effectively allows planned work to become actual, executable orders. The single highest leverage scheduling action is managing your constraint. Inventory control is all about balance. Using tools like ABC classification, YOQ, reorder points, and safety stock calculations helps maintain just enough inventory to meet service goals without tying up too much capital. Finally, measurement and improvement are ongoing processes. Metrics like OEE, OTIF, inventory accuracy, and inventory turns provide fact-based feedback, and when combined with methods like PDCA and root cause analysis, they drive continuous sustained performance gains. Thank you for joining me throughout this training. Remember, the goal of production management is not just to produce more, but to produce better at less cost with less waste and greater reliability for those who depend on your output. I hope the concepts, tools, and examples we've covered have given you a clearer and more practical understanding of how production planning, scheduling, and inventory control all work together to drive real operational results. Production and inventory management is a field that truly rewards ongoing learning. So I encourage you to explore the references on the next slide to deepen your knowledge. Applying even a few of these ideas in your own work can make a significant difference. Here are the key references that form the foundation of this presentation. For core textbooks, we relied on Heiser, Render, and Munson's latest edition of Operations Management, which offers comprehensive coverage of sustainability and supply chain topics. Another essential text is Chase, Aquilano, and Jacobs Operations and Supply Chain Management, known for its practical insights and updated content. Regarding lean principles in the Toyota production system, Influential works include Womack, Jones, and Roos' The Machine That Changed the World, which introduced lean thinking to a broad audience. Likers, The Toyota Way outlines 14 management principles that have made Toyota a global leader, while Ono's book gives a deeper look into the system's origins and processes. We also drew from theory of constraints literature, particularly Goldratt and Cox's The Goal, which emphasizes ongoing improvement. For forecasting, the classic text by Makrodakis, Wheelwright, and Hinman provided valuable methodologies. Additionally, the Apex Dictionary remains a vital resource for supply chain terminology. Finally, a note on sources. All DOI and ISBN numbers have been intentionally left out from this list, with no fabrication involved. Readers should verify editions through trusted academic or publisher platforms to ensure accuracy. This helps maintain clarity and encourages direct access to original materials. Before we finish, I want to highlight an important disclaimer. This content is designed strictly for training purposes and internal use only. Please use it cautiously, as there may be errors or omissions within the material. The author does not take responsibility for any decisions or actions you make based on this information. It's essential to use your professional judgment when applying these strategies, and for any complex legal or regulatory matters, always seek advice from qualified experts. Remember, this presentation is provided as is, without guarantees of completeness or accuracy.